In this lecture, we're going to introduce the idea of a dual pair. A dual pair is related to a relaxation. Recall that in a relaxation, the idea is to have some new problem whose optimal value is z superscript r that's related to our integer program whose optimal value is z star in the following way. In our relaxation, the space of optimal or feasible solutions is a superset of the feasible solutions of our original integer program, and the objective function value of our relaxation is at least the objective function value of our integer program for all x in the feasible space of our original integer program. This defines a relaxation, and as a consequence, we derived that the solution value of our relaxation is an upper bound on the solution value of our integer program. It performs the function of a dual bound or an upper bound. Here we're going to introduce the idea of a dual pair. A dual pair is a little bit different than a relaxation. The main point of a dual pair is that the objective function values f of x and g of u are unrelated, and also the sets that define both of these problems in the dual pair are also unrelated. So here we have a dual pair. Z is the optimal solution of the first problem, and the first problem is a maximization. This maximization is a maximization of a function over some set. The other problem has an optimal solution of w, and it's a minimization problem. And this minimization problem is to minimize a function over some other space of feasible solutions. The functions and the spaces are both unrelated. The only thing that we'd like to say about these two problems is that the function g of u is at least the function value of x for all x's in x and for all u's in u. That is, if you look at any solution or any function value inside of our space of x, it's going to be a lower bound on any value of our function evaluated at a point in u. We call this a weak dual pair. The reason we're calling this a weak dual pair is because it shares such a strong similarity to duality in linear programming, where we have a maximization problem and a minimization problem, which are duals to one another, and we would call the different spaces the dual spaces. The consequence of having a dual pair in this new sense, in this integer programming sense, is the same as in the linear programming case. Namely, our consequence is that w is going to provide an upper bound on the value z. Or alternatively, z is going to perform or give a lower bound on the value of w. In the case when w is equal to z, we say that these problems are going to form a strong dual pair. In the next few lectures, we're going to use this idea of a dual pair and introduce a few particular cases of how to generate a dual pair for a particular integer program.